This is Ms. White, and in our fifth bonding video, we are looking at orbital hybridization. The VSEPR theory is useful for explaining the shapes of molecules, but it does not reveal the relationship between a molecule's geometry and the atomic orbitals occupied by its bonding electrons. So the model used to explain how orbitals become rearranged during bonding is called hybridization. Hybridization is the mixing of two or more atomic orbitals of similar energies on the same atom to produce new hybrid atomic orbitals of equal energies. So looking at the picture, we have an s orbital combining with a p orbital to form two identical sp orbitals, and these are hybrid orbitals. So why hybridization? We are going to look at what happens in methane. Carbon has 4 valence electrons. 2 are in the 2s orbital and 2 are in the 2p orbitals. And these are available for bonding. Experimental data shows that all 4 bonds in carbon, though, are identical. So how can it form 4 equivalent tetrahedrally arranged covalent bonds by orbital overlap with 4 other atoms? What happens is the 2s orbital and 3 2p orbitals combine to form 4 identical sp3 orbitals. The 4 sp3 orbitals can now accommodate an electron from 4 hydrogen atoms. Here we see the 2s orbital combining with 3 2p orbitals and forming 4 identical sp3 orbitals which have equal energy. So in molecules whose central atoms have 4 electron domains, this is a tetrahedral electron pair geometry, this central atom has sp3 hybridization. Even if those atoms have lone pairs of electrons, such as in water and ammonia, they will still have sp3 hybridization. So if we look at methane, ammonia, and water, in all 4 molecules, the central atom has 4 electron domains. So all 4 of these molecules will have a central atom with sp3 hybridization. Again, an s orbital combines with 3 p orbitals to form 4 identical sp3 orbitals, and we have a tetrahedral electron pair geometry. For sp2 hybridization, we look at what happens in ethene or ethylene. In ethene, each carbon atom has 3 bonds, 1 double and 2 single bonds. So it needs 3 equal orbitals. So this time we hybridize the s orbital with 2 p orbitals and 1 unhybridized p orbital remains. So here we can see the 2s orbital will hybridize with 2 of the 2p orbitals to form 3 equivalent sp2 hybrid orbitals, and 1 2p orbital remains unhybridized. The unhybridized p orbital left over also bonds, but it will bond differently. We will look at that later. So in molecules whose central atoms have 3 electron domains, a trigonal planar electron pair geometry, such as boron trihydride and the carbonate ion, the central atom has sp2 hybridization, again, even if they have lone pairs of electrons. So if we look at these 4 molecules, the central atom in all of them has 3 electron domains. So we have sp2 hybridization. An s orbital combines with 2 p orbitals to form 3 identical sp2 orbitals, and 1 of the p orbitals remains unchanged. This gives us a trigonal planar electron pair geometry. For sp hybridization, we will look at what happens in ethyne or acetylene. In ethyne, each carbon atom has 2 bonds. We have 1 single and 1 triple bonds. So we need 2 equal orbitals. So this time we hybridize an s orbital with 1 p orbital, and we have 2 unhybridized p orbitals remaining. So if we look at the picture, we have the 2s combining with 1 of the p orbitals, and we have only 2 identical sp orbitals formed, and we have 2 unchanged p orbitals. These again will bond differently, and we will look at that later. In molecules whose central atoms have 2 electron domains, which is a linear electron pair geometry, such as carbon dioxide, our central atom will have sp hybridization. Here we can see 2 electron domains, so sp hybridization for the central carbon atom. An s orbital combines with 1 p orbital to form 2 identical sp orbitals, and we have 2 unchanged p orbitals. Then we have linear electron pair geometry. There are 2 types of bonding orbitals. We have sigma orbitals, and the sigma bond consists of an electron pair which is located in the region between 2 bonded atoms. The electrons are in the hybridized sp orbitals. All single bonds are sigma bonds. Here we have a sigma bond between the 2 carbon atoms, and we could have a sigma bond between carbon and hydrogen, for example. All the bonds here are single bonds, so they are all sigma bonds. Pi orbitals. The pi bond consists of an electron pair that is located in the lobes above and below the bond axis. The electrons are in the unhybridized p orbitals we talked about earlier. So pi bonds make up the second and third bond in a double and a triple bond. So if we look at the picture over here, we have a sigma bond here between the 2 carbon atoms. Then we have our 2 unhybridized p orbitals. And the pi bond is located above and below the bond axis. This constitutes 1 pi bond. So our double bond is made up of 1 sigma and 1 pi bond. Looking at the ethine picture, we have our sigma bond here between the 2 carbon atoms. Then if we look at one of the unhybridized p orbitals on each of the carbon atoms here, here is our first pi bond. There is the second unhybridized p orbital. And here is our second pi bond. So in ethine, our triple bond consists of 1 sigma bond and 2 pi bonds. So let's recap. In ethane, each carbon atom has sp3 hybridization. Only single bonds surround the carbon atoms, and the bonding electrons are all located in the hybrid orbitals. These are all sigma bonds in the ethane molecule. In ethene, each carbon atom has sp2 hybridization, and the extra electrons that are used to make the double bond are not located in the hybrid orbitals, but they are in the unhybridized p orbital. Ethene has 5 sigma bonds and 1 pi bond. Let's see. 1, 2, 3, 4, 5 sigma bonds, and the double bond makes 1 pi bond. In ethine, each carbon atom has sp hybridization, so the extra electrons that are used to make the triple bond, again, are not located in hybrid orbitals. They are located in the 2 unhybridized p orbitals. So ethine has 3 sigma bonds and 2 pi bonds. Let's see, we have 1, 2, 3 sigma bonds and 1, 2 pi bonds. Let's recap pi and sigma bonds. The sigma bond consists of an electron pair that is located in the region directly between the nuclei of 2 bonded atoms. All single bonds are sigma bonds. A pi bond can only form if there is also a sigma bond between the same 2 atoms. The electrons in a pi bond are not directly between the nuclei of the 2 bonded atoms. And because the electrons in a pi bond are not directly between the 2 nuclei, a pi bond is weaker than a sigma bond. However, because double bonds are made of 1 sigma and 1 pi bond, they will be stronger and shorter than single bonds. Similarly, a triple bond being made of 1 sigma and 2 pi bonds will be even stronger and shorter than either a single or a double bond. This concludes bonding video 5. You should have taken high quality notes. Rewatch this video as needed and ask your questions in class.